All right. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute yourself and ask those questions. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Professor Dongbin Xiu, who is a professor in the Department of Mathematics of the Ohio State University. He received his Ph.D. degree from Division of Applied Mathematics of Brown University in 2004. He conducted postdoctoral studies in Los Alamos National Laboratory, Princeton University, and Brown University before joining the Department of Mathematics of Purdue University as an assistant professor in the fall of 2005. He was promoted to the rank of associate professor in 2009 and to full professor in 2012. In 2013, he moved to the University of Utah as a professor in the Department of Mathematics and Scientific Computing and Imaging Institute. In 2016, he moved to the Ohio State University. He has received NSF CAREER Award in 2007, as well as a number of teaching awards at Purdue. He had served on the editorial board of several journals, including SIAM Journal of Scientific Computing and Journal of Computational Physics. He's the founding associate editor-in-chief of the International Journal for Uncertainty Quantification and the founding editor-in-chief of Journal of Machine Learning for Modeling and Computing. His research focuses on developing efficient numerical algorithms for uncertainty quantification, stochastic computing, and machine learning. Today, Dongbin will present an exciting topic, which is data-driven modeling of unknown systems with deep neural network. Please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton to Dongbin by asking one random question as usual. Today's random question is, what is your favorite season from fall season?
Oh, okay. Well, I guess I don't really have a strong preference, but maybe fall, because weather usually is lovely during the fall.
Nice. In Ohio?
Yeah, some place I've been to, fall is always pleasant, I think.
Nice. All right. Stage is yours.
All right. Thank you, Dr. Choi, for the kind introduction and also for the invite. I'm very happy to be here today to share some of our research in the last few years. As the title says, this is about data-driven modeling of unknown systems with deep neural networks. But I would like to make a point throughout my talk that the deep neural network is a very powerful tool we use. But what we are going to present is fundamentally is a methodology that, in principle, you can use some other techniques. But deep neural network is very, very powerful. I'm a big fan of neural network. So let me start with some motivation. This is preaching to the choir. This is something many of my friends and colleagues in national labs are very, very familiar with. That is how to analyze and predict the behavior of very, very complex systems. Here I just borrow a few slides, picture from the web, and also some from my colleague in the past. This complex system that is our primary goal for scientific computing. And they have gotten so complex that we need to incorporate many, many physical laws or mathematical models. And most of them have very famous people's name attached to them because they are very well-established mathematical equations to describe and govern with a very high fidelity of certain physical phenomena, for example, Navier-Stokes equation for basic fluid flow, right? And when we deal with very complex systems like that, climate will be the ultimate example. And our approach has always been to let's try to incorporate as many equations as possible, as more physics as possible. And as a result, and our model eventually gets more and more complex. The point I would like to emphasize here is what I would like to call, we have reached the so-called point of diminishing return. That is, by simply adding more physics and more equations to the model, does not necessarily bias too much. Yes, sometimes we see a little improvement, maybe 10%. In fact, 10% is a lot. Sometimes we barely see any. And at the end of the day, as models become more and more time consuming, and we end up with things like this. It's just random picture put from CNN, one of the hurricane forecast models. In fact, there are many, many models here. And I'm sure, as you're all aware of, each one of these curves are produced by highly, highly sophisticated, computationally expensive models. But at the end of the day, when we have prediction like that, what do we do about them? Is it conceivable, even possible, that by adding even more equations, introduce more terms in each one of these models, maybe some of them will converge to the physical truth? To be honest, at this moment, that answer is not that clear, right? So that short motivation brings us to the topic of so-called data-driven modeling. And the same message has been made by many research in the past few years. That is, it has always been data-driven, right? So in the past, in fact, especially for us, especially people in math department, myself included, that we tend to think model as nice equations, but we sometimes forget where the equations came from in the first place. They came from long time observation, sometimes take decades or even centuries of observation. And at some point, some smart, brilliant mind came into play, and they came up with nice equations, of course, named after them. And then we use these equations. These are the models we are familiar with to predict and analyze the behavior of the system. Of course, what we have already accepted that we are not able to solve all the equations. These are simple enough, but most models, mathematical models we have today are so complicated. And that's why we use computer, and that's the whole discipline of scientific computing. And so this, what I would argue, is that these days when we talk about model, the real model is in fact a piece of computer code. It's a software. And it's after all our discretization of the mathematics. No matter how beautiful the equations are, we still need to discretize them. We need to approximate them. And maybe along the way, we even introduce a bug here and there in our computer code. But essentially, at the end of the day, what's inside the computer is what we have to rely upon to predict and analyze the underlying physics. So the whole idea of data-driven modeling is that upon realizing this part, we can use computer to help us solve the equation, and realizing, again, our brain is not large enough to come up with a nice equation. Why don't we take this all the way? Let's come from the data. Let's just use the data to somehow get a piece of software, and that as a model that we can execute, and eventually let's just use this model to predict and analyze the underlying physics. So that's the whole idea of data-driven modeling, just to bypass human as much as possible. So having said all that, let me be a little bit more concrete about what I want to talk about about our research here, the data-driven modeling. So our focus is basically on dynamic system. So let's assume that we have time history of data. We call this trajectory of data. Over certain time intervals, we can have many, many of them. And we don't know the laws behind the dynamics. We do not have the governing equation. If we do have the equation, by all means, go ahead and solve them. What we want to do is that using this trajectory data, the time history, to come up with a sort of recursive model that we can march forward and predict. This would be the model prediction, the truth evaluated at the same time. This is the truth, such that our model prediction is the numerical model, its approximation would be a very good approximation to the physical truth. And if we have this model, it's as if we have the equation and we can discretize it, and it's a discretized equation, but we never will. We're not really, in most cases, we cannot write down the mathematical equation, but we do have this numerical scheme that can accomplish what we want to do, which is prediction of the future. So here we talk about prediction. I want to make a few very important remarks. Two of them are very important. One is that, and I will emphasize in the next slides as well, even though the time history data we have has time in there, we will by all means we do not want to incorporate time as an input variable. And that is, we try not to approximate x as a function of time. Why? The reason is simple. If we try to approximate function as x as a function of time, this will be our training data, or what we see. And yes, based on this, we can come up with a nice in many cases, a nice approximation of x of t, but our goal is prediction. The prediction would go way beyond whatever we have observed in our training data. And so if our approximations are coming from this, we will always be extrapolating beyond what we observe. No method is reliable when we extrapolate. So that's the point I want to make, that we will never try to think of x as function of time. Conversely here, we only think of x as a progressive recursive iteration over time. So time will never come into play. Second, what we observe, x may not be the entire complete set of variables in the system. So we do not know the system, the equation, but to make matter worse, we may not be able to observe everything. Again, climate may be the ultimate example. We can measure, wind, pressure, temperature, a few variables, but the entire climate system may, if there is a closed mathematical model, may involve, let's say, 10,000 variables. We do not have that. We can only measure a few. So this is a very big challenge. That's also something we try to observe, we try to tackle. What if what we observe, the dynamics data, is only a small subset of the entire system, which we don't have the equation in the first place? All right. So having said that, let me come back to the part of we do not want time variable in this. So this will be the example for the methodology I would describe in a moment. We only need short bursts of trajectory data, time history data. So you can take so this will be example of I say, I need 8 points along a time history. So you can pull this out from a single long measurement data. Fine. You can pull multiple pieces here. And it doesn't really matter what it is. So at the end of the day, we're going to collect them into a set of measurement of length of 8. Let's call this our training data. And you can collect, let's say, 10,000, many of them. If you have long trajectory data, time history, you can pull a lot of segments out of this thing. So we would prefer them to be from different trajectories, but that's important and yet secondary concern. The most important thing is that next thing we do, we will remove the time variable. A simple thing, we just drop them. All right. So by dropping them, we will not know when exactly this trajectory occurred in time, as opposed to goes in here. All we see are the segments of trajectory time history of 8 entries, and they all occur at a different time. Doesn't really matter to us. All we care is that we only care that each one of them is as if they start with the initial condition and march forward 7 times. That's all we care. Okay. So by doing so, we will remove the time variable. Also, it makes data acquisition collection much easier. You don't need to record the time. You just need to record their relative time. So that's what we do here. That's actually, in fact, a very easy thing to accomplish. Having said that, let me give the example how this can come into play. So this will be very similar to what I just illustrated earlier. Suppose I have time history. This will be example of so-called glucose-induced insulin oscillation, which is, as many of you may be aware, very relevant to a diabetes study. Let's assume that we have measurement of insulin response after injection for a certain individual. I have exactly 0 to 15, 16 points. I do not care about time. There's only 16 points separated by time step 0.05, certain unit. I do not know exactly what time this is, but this is only 16 points after initial points. And also I have this response at certain so-called baseline glucose level. It's a single constant parameter. Every individual have a glucose level. For me, sitting here, I have a glucose level. If I have a meal, my glucose level would be different at different level. If I go on exercise, this number would be different. It's a constant, it's an initial constant. Let's just say we can collect this kind of data at a different glucose level after injection, the short time response of the insulin, again, 0 to 15, only 16 points of this time step. Let's say we can collect many of them, okay? And it turns out people can collect a lot of data about diabetes, but let's assume this is the only thing we have. We only have at the different baseline glucose parameter level, I have the early response of insulin. We ask the question, can we build a model and understand the very long time behavior of this insulin? What happened after this early stage? So that's what we're going to do. So let's try to do a data-driven thing. We do not have equation for that. So based on what we have, I'm going to use a neural network. And at the input, I'm going to throw this single parameter into one node. And for the measurement data from 0 to 15, I'm going to throw the 0 to 14 to the early node. So I have this will be 15 plus 1, 16 inputs. I will use the very last one as to enforce the output. That's why we compute the mean square error to match the output to the 15th, the last entry of my measurement data. In between, we'll connect a very simple, fully connected feed-forward network. Right? So, and then we have all this data, and you do your neural net training. I'm sure many of you are familiar how this goes. Do a mini batch, whatever, Atom optimization, throw this in TensorFlow or PyTorch. At the end of the day, once we enforce this mean square loss to a certain level, we call this method converge. All right, so this is what then we have neural network create a model. This model would, given an initial parameter G0, given 0 to 14 input, I can recursively go forward in time, get 15. Then I can move 15 here, I slide everything backward, and I can get 16. I can recursively go forward in time for as long as I want to. So this can give me a long time behavior of the insulin. But the difference that we have now created a data-driven sort of a scalar model that doesn't require us knowledge of any other variable that's involved in this, what you can imagine, a very complex math biology problem. So the question is that we can always train a network, get a model. The question is how good this is. So let's do some validation and plot a few other initial trajectories, 0 to 15, same setting as before, at a different glucose level, each one. And we're going to feed them into the neural network model we just created. It's the one model we created. We'll never touch it again. We only execute on the different circumstances. So let's feed this initial one correspond to G0, 1, 0, put this into initial condition, march this forward in time for much longer time. This is the result we get. Everything after the circle would be what we feed into the network. Everything afterward would be the prediction by a network itself. As you can see, the network prediction would be the blue, very close to the truth. I will tell you in a moment what truth is. You can see the agreement is quite well and is reached steady state, which is obviously not very obvious from what we can observe from the initial evolution, right? This goes to steady state. Pick another curve, 1.1, and the system, again, after initial condition, the prediction by the network itself goes to steady state with some oscillation early on. Pick another curve, and yes, again, steady state. And then oscillations become a little more obvious at the early stage. Another curve, 1.3, all of a sudden the neural network says it's a periodic state, which is match the truth. And again, everything after circle is pure prediction, no data anymore. And makes a different G0 level, this become even bigger oscillation, all right? So, and you can see the match with the so-called truth here is very, very close. And now that we have this scalar model for a single variable insulin for its long time dynamic, we can analyze that. And now we see this accurate enough. I can play God mode. We can just simply interrogate this model to get all kinds of behavior out of it. One thing people study in this phenomena is that people already know that G0, the single parameter, plays the key role in determining the long-time behavior of a system. So in here is a steady state, and here is the periodic state. So what people do is that they just record the max and mean of when the system reaches the stable state. Now here max mean would be the same number. Here max would be above here, means here. And you plot this max mean against the single parameter, you get this kind of bifurcation diagram. When G0 is quite small, we have a steady state. Max and mean match each other. And when G0 passes the threshold, it becomes a periodic state, and the amplitude becomes bigger and bigger and bigger. And all of a sudden, passing here, the system returns to the steady state again. So it's quite interesting behavior. Once again, these are all blue dots are produced by just interrogating this neural net model, and the red is the truth again. So we can also do things like with different G0 single parameter, and the system respond with different. Then if I have a meal, my G0 will be at a different level. The response would be different. If I have another dessert, and my G0 gets higher and higher. Anyway, this is the kind of result people investigate in the literature. So having, once again, you can see here the neural net model has very remarkable accuracy compared to the truth. And what is the truth here? We don't really have real data. The truth in our case is produced by synthetic data. They are coming from this. So the whole thing is about insulin response. It's in some very complex math biology system, which I have no idea about. What we did, there are several models to study this insulin response. So we pulled this one from one well-established textbook. It's reasonably complex with this bifurcation behavior. This is the true model we use, and has 4 state variables and about 16 parameters. We put all the parameters from the book, everything you standard from textbook. What we did that we solved this system with these parameters, with MATLAB, with accuracy, but we record for network purpose, we record only 2 things. One is this G0, this single parameter in our modeling. The other one is the early response of I, the 0 to 15, the first 16 entries of the response. Everything else from the model, we throw them away. They are never recorded, as if we don't know. So this is just pretend in the real world, we can only measure this and the early response of this. Based on this little thing, you can see the neural net can build a model that analyzes the long-time behavior of I without any knowledge of any other variables whatsoever. Okay, the interaction, everything, you basically as if I have no idea how this physics involved, what variables involved. I just what do I see and what we model. That's that. So I hope by this example, at least is shows you that it suggests that it is possible now that we can build very accurate model and closed by itself. And this closed means the system closed. This is a closed system, right? Everything defined each other, but self-closed model for only a subset of variable, which in this case, there is not a single mathematical model to govern the evolution of I. We have to rely on other variables. For the data-driven modeling, it doesn't require that. So having said that, like I said, when we have this data, we throw them into a network. It's not a random choice we made. In fact, this work was a result of about 4 or 5 years development over this year. When in fact the example is in none of these papers. When we try the example, we actually know there is no way it does not work. It has to work. It turns out to be one of the easiest examples to train and to get high accuracy. So this is what I want to talk to you about, this so-called method, so-called flow map learning. I just call this FML, and how it works and how it gets us to the modeling of the so-called only a single variable in a much, much bigger system. So again, this is the setting. So just 10 seconds of neural network. We do not require any special uses of any special structure of neural network. All we use that neural network does at the end of the day is the mapping from input to output. In this case, would be input mapped to R8 to 4 variables, R4. And in between, in almost all our works, we simply use fully connected feed-forward network with nothing special, usually ReLU as activation function, and sometimes we use 10H. We didn't use any of this. That turns out there's no need for any of the special network. So let me come back to the basic setting. So now let me start with a simpler system, simpler problem. That is, I have a dynamic system that we do not know the governing equation. All right, so, but we do have observation of X. So we observe every variable in the system. So this will be the evolution of X. And again, from the time history, we'll pull a trajectory out of this. That's our training data. It's a fairly busy field of so-called data-driven equation recovery that is with the measurement time history of X. Let's try to recover F. We do not do that. In fact, we had equation. We had some early work on that as well. In this work, we do not try to recover F. The point being that what if we recover F with some error? I mean, F looks most likely is nonlinear. We still need to discretize it and make it into a computer code algorithm. So here, let's not try to do that. Let's again, like I said, let's do it in one shot. We want to create a model directly in one step. So we try to approximate the underlying flow map. That's where the name came from for the method. What is flow map? Flow map is a simple concept in dynamic system. It's simply the mapping between solution to one stage, T0 can be any time, to another state, T. So this is the mapping would parameterize. Oh, what do I?
Do you see something?
Something admin is right. Do we still need admin rights? I just click X. Yes. Anyway.
Okay.
Hopefully I don't drop. Anyway, so the mapping is just simply map solution from one time to another time. For autonomous system like this, only time difference matter. That's key thing. So time doesn't really matter. Right? So let's look at any solution from data from one instant to the next. And they're all separate. Let's assume the time step is constant delta t. So the mapping, this flow map is simply x mapped to the current time to the next stage, right? So that's governed by exactly same map, covers by the same parameter, which if you assume constant, this doesn't even matter here. So this is simply mapped from RD to RD, and that's what we can do with any mapping. So in this case, we only need two data from any trajectory. So you can pull a pair, consecutive pair anywhere from time to pull them out. All right. So and then I would just call this the first one x1. The second one is x2. They're all relative. Again, time doesn't matter. It's only relative position. Everywhere here is x1, x2. X1 is current state solution. X2 is the next one step later. And this is parameterized by this map, which RD to RD. The task becomes, we want to find RD to RD. Let's try to minimize this error. So I will find a map approximate map to this, such that my output by my mapping would try to match the real thing as much as possible, mean square loss. And if you minimize this problem, it's like everything like it's the least square problem. There's nothing fancy to that. Once we find this mapping, and you can now execute, given any x1, you can keep recursive going forward in time, and that will give you prediction for a long time. It's a d-dimensional function approximation. It's not operator learning. That's a key thing. Why? Because you only care about function from RD to RD, output D doesn't really matter. But as I said, it's not operator learning, which is a busy topic at this stage, is simply because, again, the fact that I said we did not ever try to write x as a function of t. If you have a little t inside, n become an operator. But now we only look at x as a vector, so it's multidimensional. Coordinate is a function approximation. For low dimension, you can do polynomial, Gaussian process, everything. In fact, if d is reasonably small, I would just say by all means go with polynomial. It kills the problem with extraordinarily high accuracy. That's in fact, our first paper on this. But most likely in practice, d is not very small. So neural network is essentially very powerful. So this is how it works. Again, if you insist, and we also advocate use a neural network. And then, of course, the network output, we just minimize this error. This is very simple, fully connected feed-forward neural network. This would be FFN. And you can also do a ResNet, which in our first paper, we advocate of doing that. The ResNet is simply says this mapping, it just doesn't try to map from input to the output. In fact, this part is mapped to the difference. And as a result, when you do prediction, you have to add this back on. Then that will be the scheme. That's the only difference between these two. They are absolutely equivalent mathematically. There's no difference, just plus minus one, depending on where you put them. But this ResNet structure looks like Euler forward stepping, except it is not Euler forward. That in fact, the entire error here has nothing to do with delta t. So this exact integrated in time. There's no temporal error, no explicit dependency on delta t. There are other errors, basically the minimization error of the training error. So in our early work, we had used ResNet primarily to, which I found is computationally advantageous. But as we gain more and more experience, we have found that this thing requires very high accuracy. At the end of the day, the ResNet doesn't really matter. So it's your choice whether you use it or not. We still keep ResNet in most of our work. It's just mostly from the legacy code. All right. So let me show you one example. Again, this example is a 4-dimensional example. So my state variable has U1, U2, V1, V2, two sort of ODE, two algebraic constraint. That's not really ODE, right? So the mapping, as I said, would be R4 to R4. It's reasonably low dimension. In fact, this result is produced by polynomial. You do neural network, you get similar result. All right. So, and this is the prediction after 1,000 steps. Again, the training data is just one separated by one step. You see extraordinarily short time history, just one step, right? And I want to make again an effort is that a point is that you look at this function, the V2 response and V1 as well. As a function of time, this extraordinarily difficult function to approximate. With the spikes like this, there's always no method that can really approximate these kind of spikes with high accuracy. Here, it is very accurate. Why? Because once again, as I said at the very beginning, we never try to approximate x as a function of time. We only try to approximate x, how it evolved over one step as a function. Right? So once you get every one step correct, it is eventually will produce you correct function over time. This is exactly how any time integrator max works. If you knew the equation, you can solve this by Runge-Kutta. Runge-Kutta looks exactly like that, except n is well defined from the equation. You know what this is. Here, we just don't know what n is. We use data to try to learn this. But the time stepper allows us to go progressively in time accurately every step. And eventually it can produce some vastly complex behavior over time, but the function, this thing as a function of time, never come into play. So that's the, again, the message I think I'm overstating a little bit, but again, this is the key feature of this method, right? So now let's move on to the very practical situation that in most cases, we cannot measure every variables in the entire system. So now let's have the whatever autonomous system that's a big complexity that we don't know the equation. We have no idea what f is. So in fact, we probably don't even have idea how many axis variables we need to have an f. This just, we have no idea, right? What we do have is that we can measure a subset of them. So z, like I said, in climate modeling, this can be temperature, can be pressure, can be density, a few things. And everything else, W, are the missing variables. We may not even know how many were missing. Is it 5, 50, 5,000, 10,000 missing? We have no idea because we don't know what the complete system look like. But we have, let's say you measure 3 variables, that's all we have. The question we ask, based on time history of these 3 variables, can we build a model for these 3 variables only? In principle, coming from autonomous system, it's possible. There's a so-called very well-known Morris-Zwanzig formula says, this kind of equation does exist. In principle, it's not useful because it says the equation looks like this. This is Markovian term, this some integral term, and that's initial condition we don't know, usually treat it as a random variable. So this is not important. What's not useful is that this formula is exact formula, but it's only sort of like existence. It doesn't tell us how to get R, how to get, most important, this K, the kernel thing. Okay, so there has been a lot of work on approximating kernel K from here. But that's based on the knowledge. We know the little f in the first place. We are trying to get to K. But here, we do not know this anyway, so there's no way we can have K. But nonetheless, we're going to use this as a motivation to design our data-driven approach. All right, so the motivation goes like this. You look at this integral. So if we want to know the evolution of z, the observables at current time, let's call it t, this needs to go back from s equals 0 with t9 minus it will be current time t. S goes to t, this t minus t will be 0. So this requires us to know the solution at current time, go all the way back to the initial condition. We're going to make a very mild assumption that, yes, this is the so-called memory. Memory doesn't go very long in most systems. So we only need to go back from the current time to some fixed time. All right, so you do not need to know your solution today or tomorrow. You do not need to know everything has happened through the beginning of the universe. In fact, in most cases, we go back to a certain amount of time. That's enough. And anything further back in history do not have any impact on the current state. That's the finite memory assumption, which is almost universally true for any system. And of course, the difference is that the key that how long should we go back, and we don't know. But that's problem dependent. But let's assume we should only go back from here back to a finite time. That's how we go. All right. So now this integral is replaced by this with some negligible error. That's the first mild assumption. Now that we change this to a finite integral that doesn't depend on t anymore, and we're just going to assume for finite integral, we can we have some kind of approximation method that can compute this number very accurately based on small threshold, based on whatever data in between these two, in between current time to backtrack the memory time. This, again, is easy because if we know the equation, we can simply do some kind of Gauss quadrature. This exists here. Of course, we do not know the integrand, but we only say, you know what, a good approximation exists. That's all we need. All right. Having said both, now we exchange this to an approximate formulation that let's call the current time Tn. If we want to know the evolution at current time Tn, we just need to know this at Tn, and this entire integral depends on everything Tn, backtrack one step, two step, whatever number of steps that's contained in the memory. That's how we do. So this is our discrete approximation to the Morris-Zwanzig equation based on very mild assumption. And this just tells us we just need to find this and this, but we don't have this. That's what we do with data-driven. We just said our FL model says in order to know one step in the future, all we need is the current time step and something go back in time. We need data on this, and if we can create this mapping, that's the model. All right, so the function approximation becomes that given this many data, so this will be n map plus 1 times d the data to this mapping. This will be our mapping. We want to find this, and this will be the network structure if we want to do. All right, so find this operator, and this will be example says I only need to go back 2 steps in memory. This is the current, this is the future. If we go back 1 and 2, and if you have data, if you have enough data of 3 mapped to 1, you have data length at least 4 in your time history, you can create input and output. And if you have many of these, you train a network, that will be the model. And the model is, in fact, coming from very rigorous derivation. So as I said here, this relationship here has nothing to do with neural network. Neural network is just a way to try to create this operator n. Right? So anyway, so this will be the example I showed you earlier. Like the instant example goes from 0 to 14, and with a 1 parameter here, and to the next. Right? So the neural network model after training doesn't really give us more results. This method eventually doesn't give it just give us a direct predictive model that we can go forward in time. How does this compare to the Morris-Zwanzig? We don't know. In fact, we're not even trying to recover Morris-Zwanzig in this case. So let me show you an example. Linear system equations. Linear system equation turns out to be quite difficult to model. It's x dot equals ax. Let's say I have 20 vector of 20. A is a 20 by 20 matrix. We come up with some random choice of this A, and we can solve them with our synthetic data. We assume we don't know anything about 10 components. We have short time measurement, time history of the first 10 components of the X. We know nothing about the 400 parameter in this system. We know nothing about the missing 10 variables. And in fact, now you can see that the 10 variables here do not give us a closed system to solve. It always requires knowledge of Q. Right? So, and we can test in this case, how long is the memory? When we create a memory, we need 0.6. Let's call this second. So it's a very short trajectory we need. We just need to see many, many pieces of this. We create a mapping, and then we're going to execute for the prediction of x1 to 10 forward in time to go all the way from 0 to 150. A very long time prediction. This will be the x3. This will be the x6. Right? So, and you can see the neural net model, which is red compared to the truth by solving the entire system, and it's very, very close after this long time in non-trivial dynamics. So it's not steady state, it's not purely periodic state, it's unclear what state it is. But anyway, the accuracy is good. Let's make this slightly non-linear. So let's deal with not very chaotic, but not very chaotic. It's a fast slow variable. So the x1 to 3 are the slow variables, and y is the fast variable. How fast this is depends on how small epsilon is. We assume that we can measure slow variable. In most cases, that's what we can. Fast variable, too fast, we cannot measure. So based on that time history data of x1 to 3, we want to create a model for the slow variables only. So this is like coarse graining, homogenization, you name it. We always try to come up with an effective model for the slow variables, the coarse variables. In this particular case, we can do homogenization, mathematical homogenization, just get rid of this. And that's the mathematical model, which is exact when epsilon go to 0, right? So here, let's fix the case epsilon is 0.1. So it's not exactly, this is not very accurate, but it's reasonably good. At the same time, we can use measurement data of 1 to 3, let neural network create a model for x1 to 3, homogenized model. And this will be the prediction of, let's say, this prediction of x1 from 0 to 200 to 400. I did not plot the first 200 because if I do that, everything cluttered looks like random noise, but upon close zoom, if you zoom in, they're not random noise, it's a deterministic chaotic system. So the first 200 plot entirely is missing. The memory is 1.2. That's the training data we have. We just need the data of x1 to 3 of length 1.2. This prediction up to 400. You can see the neural network is the red. The truth computing from the real system and synthetic data is the black. You can see the red and black track each other really, 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 really well. Okay? And the blue, which is a human created a homogeneous system, human approximation is not too bad, but you can visually see the difference compared to the truth. If we compute the error over a long time, this will be the error by our human model, human created model. Right? So now it's from 0 to 400. This typical error behavior grows over time, nothing surprising. This error by the machine learning closed model by neural network, the error is a lot smaller and a lot more stable. We do not have a full understanding of the long-time stability behavior of these neural net models, just because we don't have enough mathematical tools to understand neural network. But we have seen this kind of behavior very, very often. The long-time behavior stability can often be surprising, but in a very pleasant way. So let's make this fully chaotic. So now it's a much smaller system. Let's look at Lorentz 63. So this will be the exact Lorentz system through which we generate synthetic data and validation data. And we tried to model only X. We only have X as a data. We create a scalar model for X. But here I will show you X and Y because X and Y I can plot in a two-dimensional plot. So let's pretend here we have recorded time history of X and Y only, but we know nothing about Z. Right? So this is the so based on X and Y, we're going to use neural net, this flow map learning to create a model for X and Y only. And we need history. The history is 0.1. Time step 0.01. So this requires to have 10 steps of measurement data of X and Y. This will be the two-dimensional, the neural network model, the phase portrait. It starts from here. This is up to 100. In fact, I think it is more than 100. Anyway, maybe 1,000, I forgot. But anyways, long-time integration was. And this will be the exact model, but the phase portrait will project on X and Y. The truth, you can see visually this is very good. We don't have good point-wise error. It's a chaotic system. Nothing would track the point-wise error accurately over a long time. It's just nature of chaotic system. So here we just look visually, they look qualitatively, they're close enough. We also, based on this, the data, we compute a few measures for how chaotic the system is. The so-called correlation dimension, approximate entropy, Lyapunov exponent. These are number from the neural net model. These are truth. You can see that the number are reasonably close. I mean, they're not super close, but they're reasonable. Turns out these numbers are very hard to get stable number. They really depend on how many entries you have in your time history. It's very sensitive to that. So, but anyway, we think these are very reasonably good match. Let's make the system bigger. This is Lorentz 96, which has 40x. Right? X goes, state variable has x to 40. We only record x1 to 3, and we use neural network to produce a three-dimensional model. The history again is 0.1, so we need 10 step, with time step being 0.01. This is the three-dimensional phase portrait up to 500, very long time integration. And this is the 40-dimensional model plotted in 3 dimensions. This is, now it gets messier. It's unclear what this looks like. But anyway, this looks reasonable. And then we compute this chaotic measure. They all look reasonably close. Some numbers are very closer. And the invariant measure, the distribution that's upon steady state, again, they look fairly reasonably close. All right, so this is chaotic. So let me give you a short summary. What we did here, that when we don't have a dynamic system, there are two cases. First, if we can measure, we have time history of all the variables, it's a simple case. You just create a one-step mapping. Your training data is only 2 steps, and you can get a lot of data. Even though in most neural net training, we need 10,000, 20,000 history to train that, but this 10,000, 20,000 of one-step data. So the overall data requirement is in fact very low. Thinking about it, if you do one system prediction sometime, solve system, you can easily go 1 million steps, and you can put a lot of 2-step data from here. This is what it looks like. If, however, what your data is only partial measurement, then that requires memory. And then this will be the mapping, and you have more term on the left. All right. In both cases, we advocate the use of neural network because the dimension would be high. Keep in mind, for example, here with 2-step memory is 3 dimensions, but each z is a vector. If z is a vector of 10, this is 30 dimensions. So dimension goes high very fast. So, and as I show you several examples, it looks really, really well. We just make a quick remark that you can also model system with different controls and all excitations. The key of this, there's some modification had to go into that, but at the end of the day, you can train your neural network model based on some control. Then the prediction, the control can be entirely different. That's never ever present in your training data. So this is a very remarkable property we have harnessed from this thing by looking at one step at a time, never have time involved. That allows us to do that. So this paper has a detail on that. So I don't have time on this. I want to give you not just a few minutes, a quick idea on how we do this with PDE, because we have discussed so much about dynamic system. Right? PDE is what people really care about. So now it's a similar setting. Suppose I have a set of grid on which I have data, right? So the data is now it's a field. So this is, I can think of my observation as one vector field. If this is the finite element solver, your grid would be a vector of length, let's say 10,000, if you have 10,000 nodes in your finite element solver. So it's one big vector. Suppose it's autonomous, suppose we observe every view, and now it's fully observed system. It's just like ODE. Upon discretization, PDE is ODE. And nothing is missing. So we just need to map from current state to one step later. If we have this, we can create a map and we can solve this, learn this unknown PDE, right? Turns out it doesn't really work. We tried this many times, no less than 1,000 different cases. It just didn't work. Why? Is because in dynamic system, the mapping between these are the state variable x. X is just vectors. They're components of vector. Nothing we can say about it. It's a dynamic system. For PDE, it's different. The U's are solution in space. They are not random components of a vector. U has smoothness, has regularity. They are connected through them because PDE has operator in them. So there's a smoothness, regularity in there that we are not enforcing here. That's, things, when I say they don't work, they don't really not work. They just work sort of inconsistently. And without the high accuracy I've shown you throughout this work, we really demand accuracy to be high. So we eventually tried convolution network, still didn't quite work. Again, no less than a few thousand test cases, still didn't quite work. So we eventually were forced to develop for the first time a network structure to enforce something. Again, it is motivated by the mathematics. Right? So suppose I have a PDE like this, involves some kind of differential operator. I don't know what they are. I don't know what L is. I don't know how many. But suppose I know the PDE, and suppose I have a set of grid. I can solve this by some kind of Euler forward. I'm not going to do that, but Euler forward does exist. Right? So one-step mapping from here, this would be my operator, and each derivative would be replaced by some differentiation matrix. That numerical analysis tells that everything linear, matrix vector product for derivatives. This would be my very naive Euler forward. Its stability would most likely be an issue, but we're not solving it. We just need this to be on the conceptual level. It exists. It gives me some kind of truncation error, one step. And we just say that since we don't know this, we don't know the derivative, I would just say, you know what, we can make every differentiation matrix a nonlinear vector operator. It doesn't even need to be linear operation. If I make everything nonlinear, it's incorporate this as a special case. So the existing Euler forward says there exists an even bigger class of nonlinear scheme such that my error, one step error, could be smaller. It at worst would be like this. So it's a special thing. We're just making this class of method sort of nonlinear Euler forward much bigger, much broader, and we are saying that the error we commit over one step most likely would be smaller than this, but at the worst case, it would be just like this. Why? Because I can simply put this back into my linear matrix that exists. So that's all we need. So this we see this nonlinear or forward method does exist like this with some operator we don't know, and this operator corresponds to L. This is how we design our neural network structure. The input, one-step input, the vector over a finite element grid is here. The output is here. In between, we have a sort of neural network in parallel goes in this way, in parallel, in this direction. Each one corresponds to some kind of nonlinear operator that we do not know. And then I have another network horizontally here acting component-wise against all of them. This is a nonlinear operator here to learn the L here. And if we connect this together, that I can train. And this one works consistently. In fact, without this layer, what we call assembly layer, up to here, this stage, it resembles convolution network very much. All right, so this is the key. This is what we call the assembly block. The assembly layer is what really makes everything work to enforce regularity, things like that. Let me quickly show you a few examples. Again, the equations here only serve the purpose of generating training data and validation data. So the equation may be simple, like ut plus ux equals 0. The simplest equation analytically, perhaps the most difficult one to solve accurately numerically. Again, everything here just rely on one step, a vector. Here we have 50 nodes. It will be the vector of 50 to 50 mapping. So there's nothing missing, just one step mapping. In between have the assembly block. And this will be, prediction over a fairly long time, 20, t equals 20. You can see the accuracy quite well. In fact, the dispersion error is much, much better than we expected. Many numerical methods, if we know the equation to solve this by some standard numerical method, at T20 will show worse dispersion error. But here it's just by learning the equation. Advection diffusion doesn't really matter. I just want to show you that it works with non-uniform grid. In fact, in this case, that the grid is not only non-uniform, they are also randomly permuted. This method doesn't require any knowledge of the physical structure of the grid. The geometric structure connection is not required. You can deal with higher derivative. This is easier case because it's more diffusive. Diffusion equations all be easy to simulate. Integral equation which effectively make this non-local problem again is diffusive, so it's very easy. Accuracy is good. Berg's equation, it will be an interesting example that again in this case when we generate the training sample, we have 50 nodes. We solve this by some. We actually don't at the beginning. We solve this analytically, and that means that our training data is created by some randomized Fourier series, sine cosines we created. They're finite series, so they are very smooth. We solve this by 1 times that, which is 0.01 or 0.02. Nothing happened, or 1 times and no shocks whatsoever. So that's our training data. All our training data are smooth sine cosine over 1 step, which is also smooth sine cosine. Upon learning the operator mapping between the 2 steps, if you execute this on a new initial condition over much longer time, when the shock will appear, it does appear. So that's the thing I would like to emphasize here again, is we do not need to see the physics in order to predict the physics. In fact, if you recall, in the very first insulin example, this already showed that none of the early stage, the insulin response has steady state or periodic state. You never see that in training data, but over long term, if you have the correct model, it will produce the correct physics. The physics is always very short time dynamic. It doesn't have any interesting physics in the short time. In over 1 step, almost nothing happens. To make matter a little more interesting here, we assume that we can only observe grid value at right half, in fact, 40% of the domain. And in this case, we actually do need to use memory because these 50 vector 50, we only observe 20 of them. So a missing 30 component is missing variable. We have memory, but with sufficient memory, you can still predict physics in here. And this accuracy isn't that high, but we say, in this case, with shock and 40% domain, I will give this a pass. So let me just finish. Can do 2-dimension unstructured grid. This will be 2-dimension, but this PDE, but the entire 1 set of variable completely wiped out. We only have data of V. This is very expensive. This is like 50 by 50 grid. So the vector will be 2500 length. And with memory, I believe we have 10 memory. So this would be 25,000 input for the neural network. So it's a little bit expensive, but at long-term prediction, the solution goes up, down, sort of periodic with a little bit diffusion. And you can see the reference prediction looks fairly reasonable. So anyway, let me finish. Time is up. What I have discussed is what I call the FML, the flow map learning. It's a method, it's a methodology. Again, I want to emphasize it's not, it shows some capability that was never really, we didn't really thought about before. For example, if we can model only things we observe. So this would be very useful if we try to do some kind of multi-scale modeling or try to speed up computation by only predicting the cost variables, which goes faster. Or you just blindly say, I only see this, I model this, right? So without worrying about any other variable that may or may not couple with the things we want to model. But this capability, if it's new in certain way, like I hope this talk has illustrated to you that it's not because the neural network, it's simply because we set up the problem mathematically correctly. And we set it up as correct mapping from input to the output. Neural network is a very, very powerful tool, one which I'm a big fan of, but it's not what brings the magic. The magic is about setting that properly. And in most cases, our network is very small. It's not really deep learning like this. It's not very deep. But anyway, there's no really need to use special structure. The thing with memory, one may ask, some of you may ask, can you, a famous network structure that incorporates memory is LSTM. Can you do that? Yes, if you have missing variable, if you do LSTM, you can accomplish about the same result. We have a collaborator who has tested this sort of extensively. But then it's back to the question in our case, if we know how it works, why do you need to introduce this structure with a gate and everything? It's a small plain network would get it done. So anyway, one big thing I would emphasize is that, and for many of you who have done neural net training, who really are high on the accuracy of things, you know how hard it is to reproduce the result. For students who have trained network, you train that today, tomorrow it may not be the same. You pull a code from GitHub, from somebody's paper, and you try to replicate the result, you cannot, whose fault it is. So in our group, reproducibility is the number one criteria. A good result or bad result better be reproducible. So we're in the process of organizing almost all the examples I discussed here in this talk and many of our papers to put them online, including the training data, how to generate the synthetic training data set. In fact, the training data set we use to generate example. More importantly, we're going to put the data we used to plot the plots so that you can replot what we had in paper immediately and then compare to your results. So I'm also in the process of writing a very detailed paper describing the computational detail, the arts, how to create reproducible plots. So anyway, all of this will be available. It's in the process of getting uploaded at the moment. I have a new website it's in the making, but anyway, this will come up in just a few weeks. So with this, I will finish and take some questions.
Thank you. Thank you so much, Dongbin, for the wonderful talk. I enjoyed it a lot. I'm sure everyone else enjoyed it a lot as well. Although it's 11, let's have a Q&A session. Dongbin, I hope you have some time.
Yeah, I do have some time, so I don't know how to see chat. So.
Yeah, well, don't worry about it. Okay, so Pat, are you there? Are you still there? I mean, you post a lot of questions and
I did, and
yeah.
let's just take the most important ones.
Yeah, exactly.
There are other questions too, that from other people. So you seem to be assuming that neural nets are the way to go here, rather than trying to discover the equations themselves in some interpretable form. And there has been a lot of work for decades on that approach. So could you now? I mean, and of course, there's also been a lot of recent work on using neural nets to do similar kinds of things. Could you just talk about the pros and cons and why you think that this doesn't have to be better, right? This could be just one among many approaches, but you did suggest at times that you thought this would be better than other approaches, including implicitly better than learning the equations directly. What's your opinion on this?
So yeah, so I did say that neural network is very powerful. Again, like I said in this, but you don't have to do neural network. So neural net in all these things we did here, it's just a tool to accomplish this kind of mapping. So it's just a way to accomplish this mapping. Like I said, if the dimension is low, polynomial will kill it. Polynomial is the king. But I am a fan of neural network because many of cases the dimension is very high, the input nodes, and so let's do neural net. So I do say neural.
Why do you believe that neural nets would be better than, say, trying to discover the equations in classic ODE form?
So that's had nothing. So again, it's I want to be very clear. I will advocating getting this of model neural net, or it can be polynomial, can be neural net, as opposed to discover F in the so we have done similar things. So let's say you want to discover F. So let's just assume you can discover F analytically correct. All right.
No, not analytically. I'm talking about inducing it from the data in the same way you are with the neural net.
Yes, that's what I'm saying, that if you can induce F from data, first of all, you can never induce F exactly correct. You have error in the first place, right? And then you have to discretize whatever the approximate F to solve it. You induce another error, so error compound on itself. You're solving sort of slightly wrong equation in the first place.
Just to be clear, are you saying that, forget about whether you're doing neural nets, it sounded as though you, rather than learning a differential equation or a difference equation, whether it's in neural net or other form, that you're learning a mapping directly from the values at one time step to the next time step.
Correct, yes.
Because you're not learning the difference. You're learning to predict.
That's my point. Regardless where you come from, you can try to use your data to recover F, to do other form. At the end of the day, your prediction look like this. One step to the next is a mapping. So that's what we just try to go to this one-step mapping in one shot. Because I wouldn't
use the word one shot there because it's overloaded.
No, one shot means I have my data. I want to create this one-step mapping in one step. That's all.
Sure.
So, as opposed to separate the tasks, we introduce error in different stages. They compound each other, make their. At the end of the day, is xn plus 1 equals x, some kind of xn.
We should follow up separately. I've got your email address. Someone else had a question about noise.
Noise. A very good question. Noise. There are two kinds of noise. One is the standard measurement noise. If for example, in this slide, if I have x1, x2, both have observation noise, this is easier to deal with in the sense that you just do, because at the end of the day, the learning part, the things I discussed here is really about minimizing the mean square error. So let's just do this. Yeah, so it's about minimizing the mean square error. So we know it's the least square is sort of robust against noise.
Well,
if we reduce the accuracy. The accuracy that I showed you here.
Right?
Sorry.
Have you added noise to synthetic data and shown that?
Yes, we have. Our paper, I only showed you here without noise because I want to show the accuracy. That is fundamental understanding. So in some of our paper, we do have a noisy data example. The accuracy will be less as expected, nothing to that. So, but there are other things we do not fully understand sometimes. So the other type of noise would be if your equation has stochastic thing driving it, that will become SDE. That's entire different things. That we have less understanding. We only have the very first paper just recently wrapped up. I'm not ready to discuss that in extensively yet. We have some understanding, but we have struggled with SDE for quite a long time. So
okay, you said it early in the talk. You said, let me see what you were talking about not having time as part of the learned equation. Right. And I thought you meant by that you were simply making the Markov assumption that you did not have memory. But then later you introduced memory, so I figured that I misunderstood you. What did you mean in the early comment?
What I meant is that which is the what's the best? What I meant is that for example, if this is a neuron, so let's look at this. My input x and x, so we should never have t as an explicit input. So for example, I do not want to measure x as a function of t. I should never have t as a node in here.
Okay.
Yeah.
And that's not the same as making the Markov assumption?
That's not.
Okay. So, it's if you make the Markov assumption, that's true, but it's weaker than that.
But they're all Markov, right? So anyway, just how many steps.
System with memory is not making the Markov assumption.
But depends on how you define Markov. This one-step Markov, multi-step Markov. So.
Oh, I see.
Yeah.
Okay.
Yeah.
Fine. But so Yes. Well, I think I don't. That's not controversial. I understand now what you meant.
Yeah. Okay.
And
All right.
and go ahead if there's any others. There were definitely some others down below.
Yeah. Well, I want to invite the Rob Hayes. He asked about the noise data, but he also asked another questions. So Rob, if you want to unmute yourself and ask your questions directly, that would be very helpful.
Yeah. So it came down to it looked like the process you're describing does require each successive data point to have the same time step. So you're not folding the time step in, you're not mapping it with that, but they do require sequential time steps to be equal for all. Okay, that's
a good question. We have not worked out for simpler cases. We can do variable time stepping, but for this with memory, we don't know how to do that yet. So it's a requirement at the moment.
Got it. Okay. All right. Seymour, are you there?
Yes, I am.
Yeah. Can you ask me a question directly?
So I had a question regarding just a comparison with other time series forecasting methods. I was curious if the methods that you propose, if they are comparable or are better than other conventional time series forecasting methods. And if we have time, I have some other questions about your other papers, but it's probably going to be outside of the scope of this talk. So
right. So we didn't do comparison with other time. Yeah, there are a lot of statistical method to do that. We didn't do that kind of comparison. I would guess, look, this kind of thing is hard to get with other method. Right? I think, I don't know, I'm not aware other method can get this kind of accuracy with this little data over this much long time, to be honest. If you are aware of some, please let me know. I would be more than interested in looking into those methods.
Okay.
But I wasn't aware. We didn't do any comparison. So
yeah. Thank you very much.
All right, sounds good. Fei Zhao, are you still there? All right, Fei Zhao, we heard you. Can you volume up? We barely hear you, Fei Zhao. Well, I can just ask. Okay, Fei Zhao asked, in the fast-slow example, the GT and your NN do not diverge. Does it imply Lyapunov exponent of 0? That's what he asked.
I do not know, to be honest.
All right.
I don't have a good answer for yeah.
All right. Sean, are you still there? Sean Smith from Los Alamos. If you want to ask a question directly. Otherwise, I can ask. He asked, the motivation of this approach is that to use mathematical computational tools to circumvent the necessity for physical modeling. However, definition of the state space that you rely on is a large proportion of the physical modeling, even when provided by experiments. Selecting appropriate instruments requires insightful physical understanding. Even when the state space is only partially defined using Mori-Zhuanzig, the selection of the subset of the state space is even more critical. In each of your examples, the state space was defined by a physical model. Do you have any comment on that, Dongbin?
I'm trying to understand. So it's a question.
Yeah.
Is it? If I guess, is it about how to select what variable in order to understand the physics? If that's the case, I think it's a slightly different problem, right? It's an important problem. So a question to ask, even for partially observe, what variable I want to observe in order to understand the dynamics of the problem. And the method here is just assuming that's what you observe. So the limiting case that what if I observe something that's completely useless? I see nothing happens. For example, I observe for a moving vehicle, I observe the vertical location of the vehicle, which is 0, never changes. Well, this method just said, you give me that data, I'm going to produce the prediction of 0, the vertical location, which will always be 0. So which is still correct, but the useless results. So I think these are slightly different problem if I understand what you ask here. So identification of the variable to measure, and this is an important but a different question. Here is just, if you observe this, we're going to predict this, which may be useless if we observe the useless variables. I hope I understand the question.
Sean said thank you. So
Okay.
sounds like, yeah, you answered them correctly. Well, I don't see any other question, but I have a couple of questions.
Okay.
You know, when you extend your method to the PDE, and you gave the nice examples and how, gave us an insight on how to extend your FML method. So you have introduced, you can do so using some linear map, but why do you stick with the linear map? Extend it to nonlinear map using the neural net in spatial.
You mean this motivation?
Yeah, exactly, right?
No, we didn't use this. We just that this thing exists. It's let's take this all of four. Let's see. It's the worst case a neural net can do, because neural net would make everything nonlinear. So it's just motivation. It's how we design the network structure based on this, because it's just after no less than a few thousand testing cases when nothing really worked consistently. We're just trying to find ways to see maybe we need a structure, so we didn't know what to do. So we look into all forward type of thing, and then we decided based on this to design neural net structure mimicking this.
Exactly.
Like I said, yeah.
Exactly, and then you change the differentiation matrices to nonlinear functions, and by doing so, you're effectively introducing, the space which is a lot bigger than just the linear.
Right, it's bigger than that, so it can be a nonlinear map.
So in some sense, the training will be harder than
training will be more expensive because now we have the block thing. So input, output, forget about this little thing that we have this parallel layers, network layers here, and then this thing goes vertically on component wise. So training is a little bit more involved. It's mostly because for PE, the vector is much longer. That's actually the killer part.
Right.
So in fact, when I said in my, if I can add in my finishing slide, when I say most of our network simple, small, apply to this case, when we do PDE here, input one step. For this, we usually just go with one layer. Here we go one layer like in this thing. It works remarkably well. And in our paper, we actually did 2 layers simply because I told my student, look, if you don't do 2 layers, people will ask, why don't you go deep network? So it's just one layer works fine. So the moment it becomes nonlinear, it works well.
Okay. Well, I was wanted to ask, there sounds like there's a trade-off between, you're making the training harder, but in some sense you're increasing the dimension of the parameter space. So you're hoping that you will get the better model at the end.
In principle, we hope that, yeah.
Yeah. So I guess that's the trade-off you're talking about here. Oh, by the way, the last slide, examples, you said the PDE with the missing variable.
Right.
It looked like a PDE with the missing equations, not the variable.
Well, if it's, it's an entire missing equation. It's a variable, right? This is 2500 V, 2500 W. We're missing 25. If you think the entire PDE has 5,000 things, we are missing half of it. So yeah, it's a missing variable, right?
But the
it's
first
missing
thing,
entire PDE.
Entire PDE equations, but the first one, you still have a V and W, all of them.
Right, it's coupled together. So we don't have W here. It's a model of V only.
A model of V only? Oh, okay.
Yeah, this is only for V. That's nothing. We only observe V. We don't have W whatsoever.
Oh, got it. Oh, okay. I misunderstood this slide.
Oh, okay. Yeah.
All right. Sounds good. I'm sure there are more questions. I personally do, but I think I can ask that
Yeah, please, if you have interest in this, please feel free to write me email. I'd be more than happy to discuss offline, online, offline to this talk. So I'd be happy to answer any question. Explore some possibility to work, collaborate as well. So
that'll be awesome. Yeah. All right. Thank you so much.
All right.
Let's thank our speaker today and for the wonderful talk.
All right.
And as Dongbin said, hopefully there's a future collaboration between us. All right, sounds good. Thank you, Dongbin.
Thank you very much. Thank you for the invite. Okay, bye.
Okay, bye.